So it's a pleasure to have the first colloquium planned to be given here. I mean, we had another accident where we used this room, but this is the first time we actually used this willfully. And it's an honor to start with Professor Steve Gubser from Princeton University. He was born in Oklahoma, but he spent many years. He grew up in Aspen, where apparently he even sang with John Denver. There must be a recording of there, even though nobody can find it. So John Denver, I don't know if it's John Denver, Steve Gubser, Christmas Carol. That's enough to find some.
It doesn't seem to exist on YouTube, but I claim it exists.
He studied physics also, and he studied he did all his studies in Princeton, right? Except for a stint in Cambridge University, but his PhD is from Princeton, and then he moved to the Harvard Society of Fellow, and he became assistant professor of physics in 2000. Shortly after the famous paper on string theory, which is on ADS-CFT, on which he's one of the authors. People at the institute actually wit and say, I feel I was partially scooped. So I don't think that many people can have wit and say that about them. So indeed, they arrived first, Stephen collaborators. He went to Caltech as professor of theoretical physics, but then came back to Princeton as associate. So maybe because Princeton is like the Imperial Guard in old Russia, where the colonel ranked as a general elsewhere. So, and he was promoted general of Imperial Guard, or professor of physics at Princeton in 2005, and he has been there since. He has received many awards: a Simon Fellowship, a Guggenheim Fellowship, a Blavatnik Award for Outstanding Young Scientist, the Gribov Medal from the European Physical Society. I can sympathize because he also served as director of graduate studies in Princeton. Lucky for him, only for 3 years. And so it's a pleasure to have him today, where we talk about number theory and space-time.
I may add that many years ago, who awarded him first prize for undergraduate.
Yes, and actually with a talk that also involved number theory in a sense, right? Was about the Fibonacci numbers.
I had some work as a junior on Fibonacci numbers in Philotaxis. I think that the work you were thinking of, I think, was matrix models.
What?
I think what the Apter Award was for two-dimensional matrix models of two-dimensional
I don't recall the details, but I remember we were very impressed.
Thank you. Well, it is certainly an honor to be here. Thank you, Massimo, for that kind introduction. I actually haven't visited you guys since you moved into your new building, and it's very impressive. So I want to tell you about work that I've been doing with a lot of students, including Matthew Heidemann, Christian Jepsen, Ziming Ji, Johannes Snaut. Matilda Marcoli is faculty at Caltech. Sarthak, my student, just moved to a postdoc at Caltech. Ingmar and Bogdan are postdocs as well. Brian Trundy is my student. Anyway, a distinguished lot of students. And what I want to start with, in the spirit of giving a sort of general context at colloquium level, is just to ask the question asked so many times: why is quantum gravity hard? And I'm going to give you the standard answer. That scattering of gravitons becomes more powerful at high energies. And you can see that because Newton's coupling has dimensions of area. And so to get an invariant amplitude for the scattering amplitude at tree level, you need to multiply the Newton coupling by 2 powers of the energy. And that's really disastrous when you enter into loop diagrams because, at least naively, large loop momenta will dominate the diagram. And if you have L loops in your diagram, again naively, you would expect that the overall loop amplitude should scale as the Lth power of this very large number, large at least if the cutoff lambda is taken very large. So, as I said in the transparency, ever more powers of lambda seems to indicate certain depth in a normalization group analysis. And so you would really like it if some of these powers somehow went away. And miraculously, actually, some of them do, especially in very supersymmetric theories of gravity. There's even the conjecture out there that maybe in some sense all of them managed to go away for the most supersymmetric theories of gravity. But that still remains unproven. And I would take the conservative point of view that even in the most supersymmetric theories of gravity, just as local theories, you're eventually going to be overwhelmed by these positive powers of the cutoff, and gravity is non-renormalizable, and quantum gravity is impossible. It's tremendously different from another theory where invariant amplitudes scale as the square of energy, the classic example of Fermi's theory of beta decay. Here would be a beta decay according to Fermi's theory, with G Fermi, which has the same dimensions as Newton's coupling, at the quartic vertex. And everybody knows the way that is resolved at small length scales is that this is not a point-like interaction. You have some scale across which a W boson is capable of propagating, a very short scale, because the W boson is very massive. And you wind up with a renormalizable theory of quarks and leptons and W bosons, and well, that's the standard model. So, what's the lesson? A non-renormalizable interaction, like the Fermi interaction, tells you that something new is happening at some high energy scale or some small length scale. And so we've been trying to learn that lesson since forever about quantum gravity. We've been trying to learn the lesson that somehow at the Planck scale, something new happens to gravity, which is very different from what we know and love in Einstein's theory. But what could it be? Amazingly, Riemann had very relevant thoughts in this direction. I'll pause for a moment so you can read his quote here. This apparently was in the habilitation of his doctoral dissertation, which comes late in the old German system. It was only less than a decade from his own death, tragically. But what an insightful idea that having just invented all of differential geometry, okay, following Gauss, he suggested that it might not go all the way down. That at some very small scale, there could be some simpler explanation of phenomena in terms of something non-geometrical. And we are still looking to complete that thought of Riemann's from over 150 years ago. So, let me wend my way toward a proposed direction toward answering Riemann's thought. I'm going to wend my way through a bit of the gauge string duality and p-adic numbers, and then I will combine the two, and then finally I'll try to bring it into the ambit of geometry and get back to this notion of Riemann that perhaps the continuous geometry that we know and love might not go all the way down. So what about ADS-CFT? It's certainly a high water mark in non-perturbative string theory, and the way it goes more or less is that you have some bulk space-time which is curved, negatively curved, that's very important, in which a supergravity theory lives and dictates the dynamics of the bulk geometry. This is a smooth geometry in here, some smooth Lorentzian space-time fluctuating according to the classical equations of supergravity, which is a limit of string theory. This negatively curved geometry has naturally a boundary at infinity on which a conformal field theory can be made to live. And you can think of the stress tensor of the conformal field theory as a kind of creation operator for a graviton of the bulk theory. So this boundary composite stress tensor, you can think of it sending a graviton into the bulk, and then another insertion of the stress tensor on the boundary soaks up that graviton, and that tree-level propagation of the graviton through the curved geometry somehow, through the magic of the gauge-string duality, manages to compute for you the two-point function of the composite operator, the stress tensor, in the field theory all by itself. So I'm thinking of gravity now as a tool to compute a correlator which might be difficult to compute directly in the gauge theory. But the story, the underlying story, at least in my current way of thinking about it, is that the gauge theory is this fundamental thing, and we're just using gravity as a tool. The gauge-gravity duality claims more. It claims that the entirety of the physics of the gauge theory on the boundary is equivalent to the entirety of the gravitational theory in the bulk. So in particular, any correlation functions that you want, for instance, correlation functions, for instance, of three scalar operators, could be computed through some process in the bulk. Here I've drawn the simplest three-point process in the bulk where some quantum comes in and scatters with the three-point vertex, as you see. And the characteristic feature of this kind of amplitude and this kind of three-point function is that the final answer is a simple power law of the arguments, as I've indicated. What else is prominent about ADS-CFT is that it gives an account of black holes in anti-de Sitter space. And part of that story is that there is an entropy of the CFT which scales as the cube of temperature. That's because of conformal invariance. This is as a dimensionless quantity. Temperature is the only scale in the game in a conformal field theory at finite temperature. So you have to multiply t cubed by v to make things extensive. And then the factor of n squared comes in because there are n squared different gauge bosons in the particular gauge theory that we're thinking of. Anyway, this conformal field theory entropy matches to within a factor very close to 1, but not equal to 1, with the Bekenstein-Hawking entropy of the black hole horizon. And that slight mismatch is because the calculations here can be done at weak coupling, and the calculations here are done in gravity, which turns out to correspond to the strong coupling limit of the gauge theory. I'd like to get somehow to quantum gravity, which is where I started. And in fact, in ADS-CFT, there are efforts towards quantum gravity, but I would say they're relatively feeble. An example of what we can do in terms of quantum gravity effects in ADS-CFT is that we can compute loop corrections in the bulk to the tree-level graviton propagation that gave us this two-point amplitude of the stress tensor. Those loop calculations in the bulk, they are, after all, quantum corrections, correctly tell us that the stress tensor two-point function has in its numerator not the square of n, which is the rank of the gauge group, but instead n squared minus 1. The minus 1 is a loop correction. And that minus 1 is the sort of precisely correct counting of the number of degrees of freedom of the gauge theory. So, okay, there's some perturbative control over quantum gravity in ADS. That's impressive, actually. It's a hard calculation. But we seem hardly to the point of understanding the deep question of why is quantum gravity hard? What happens at the Planck scale in anti-de Sitter space? With all the power of ADS-CFT, I don't feel like we're really much closer to answering that question. So, time for something completely different. P-adic numbers. I hope in another couple of slides you'll see why I think of p-adic numbers as particularly conducive to ADS-CFT. But for the moment, let's just review what they are. I say review because they've been known for 100 years and more, even though I certainly didn't know about them 5 years ago. P-adic numbers are a superset of the rationals, just as the real numbers are a superset of the rationals. So here are some sample rational numbers. you adjoin to the rational numbers the irrational, so square root of 2 and pi and e to get the reals. All right? In order to get the two-adic numbers, you adjoin not the square root of 2 or pi or e, but you adjoin instead some sums like this one, which look like they're infinite. You adjoin lots of sums that run to arbitrarily high positive powers of 2. That's kind of the characteristic of a two-adic number. So they all look terrible from the point of view of real numbers. They're not real numbers. But as we'll see, they're legitimate things in their own right when you look at them in just the right way. And they're even physical, I claim. Again, if you look at things just right.
So it's the, where does it shift from being just a power to being a sum of powers?
That's where I'm saying the two-adic numbers are a superset of the rationals. And so if I only had finite sums, then I would only get, in fact, a subset of the rationals. Maybe the rationals whose denominators are powers of 2. I could do that with finite sums, but then I want to say, oh, let me just have all the sums that have arbitrarily positive powers of 2, but I'm not going to allow arbitrarily negative powers of 2 in the sums. So they're always one-sided, but they go kind of in the wrong direction. Ordinarily, you would say that you want your sums, if they have infinitely many different terms like this, they'd better get smaller and smaller in order for the sum to converge. But I'm going to break the rules and go the other way.
Sorry, there's the dot dot dots and the n. I mean, I should put in all. I mean, the one is a sum from n equals 0 to infinity, so that's just one extra element.
Sure. Okay.
And then 2 to the n, I should imagine that's all the different values of n equals 1.
I tell you what. In order to get the dot dot dot, instead of including all of these powers,
Right,
why don't we just take some of them, but as many as you like, infinitely many. Every other one, for instance, every third one, a random selection.
Okay.
That gives you all the two-adic numbers.
Okay, but you're not pending this, okay, sorry, and then there's.
Yeah.
So then the 3 and the 5 would be
Powers of 5, powers of 3.
Those would be
And then what
called
about
three-adic.
Exactly. And then you might say, oh, why the heck not powers of 6? And there's a reason for that. I'll come to it.
What about infinity?
What I would say is, if you want the 5 adics, you can allow arbitrarily positive powers of 5. If that's what you mean by infinity, then sure.
No, what would you call R to infinity?
Oh, it's just something that number theorists like to do. There are some reasons for that, but I think it's mostly just a convention. I sometimes use that convention just so I don't have to write R. Oh, anyway.
I think what's confusing is, for example, what you're calling Q2, it looks like it's not fully specified yet. It's like you're telling us, take some random set.
It's specified. It's a set of 2 to the n closed under sums. The sums could be infinite, right? Period.
But only infinite in the direction of having more positive powers. But I'll come to it. You're right. There's something a little bit missing from the game. And I should emphasize here that I'm hardly the first person to suggest that p-adic numbers are the answer to life, the universe, and everything. This Russian crowd has been saying this in very interesting ways for a lot of years, and they have a book on it. Okay, so another way to say this is that you can have a decimal expansion, let's say a binary expansion if p equals 2, which runs arbitrarily far to the left. That's another way of saying the same thing, that we're including arbitrarily positive powers of 2, and maybe only finitely many negative powers of 2. Perhaps we only go 2 steps to the right of the decimal point. Now, why is this an okay idea? It's because, here's the crucial point, it's because you can define a norm that makes these sums convergent in the sense of that norm. Here's how you define the norm. We can define it just on ordinary rational numbers. So you say the norm of 0 is 0. The norm of anything else is positive, so it's a Euclidean norm. The norm of p itself is 1 over p. So p you're thinking of as small, not big. And if you multiply p by itself, its norm becomes smaller. And then the norm of anything prime to p is going to be 1. So for instance, this p-adic number, which has 2 points after the decimal point, 2 digits after the decimal point, has p-adic norm p to the plus 2. Pardon me, there's a plus there, not a minus. It's plus 2 because it's got a negative second power of p here. And if p is small, then 1 over p is actually fairly big. How big is it? It's the norm of 1 over p would be p. The norm of 1 over p squared would be p squared. So this is very big, fairly big, medium size, smaller, 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 in the sense of the p-adic norm. So now you can see why I'm okay with continuing as far as I want in this direction. But it sure seems weird. Still, this is a legitimate norm in the following sense. It has a triangle inequality, and it has this multiplicative property. And so you can start with the rationals and complete them with respect to this funny norm, and you get the p-adic numbers. That really is a full specification of the p-adic numbers. It still seems very unsatisfactory from a physicist's point of view. Feels like a cheat. Let's just get a little bit of practice, and then I will turn to how p-adic numbers could be physically realized, at least in principle. Okay, so here's the p-adic number I suggested at the start, just the sum of all non-negative powers of 2. I claim that this equals -1 for the sort of obvious reason that it's a geometric series, and so you can use this funny identity, which doesn't look right because it's outside the normal region of convergence of 1 divided by 1 minus x. So it, again, looks like I'm not playing fair. But you can make it work without fudging through the following operation. You say, let's write the binary expansion of this thing. Here's the decimal point. I didn't write it. Here's the decimal point right here. And then you have 1 all the way to the left. And now we add just 1 to this big, huge, infinite sum and do it in binary arithmetic. Each column goes like this. 1 plus 1 is 2. That's 1, 0 in binary. So you put the 0 here. You carry the 1. Add the next column. You get 2 again, which is 1, 0. Carry the 1. Keep going. There you have it. It's 0. Just can't argue with that. A crucial point is I'm carrying to the left. So it's not like I just took a real number and flipped it, because if you added 2 real numbers, you carry to the left in the ordinary addition. But after flipping, if you did the same addition, you'd be carrying to the right. I insist on carrying to the left here. And that makes two-adic numbers really different from real numbers. They're a different beast, but they are legitimate beasts. Okay, so I've told you what they are. Now let me try to convince you that you should be interested. So imagine an Ising spin model with 8 sites on a circle. And I want couplings that look like this. Spin 0 is strongly coupled to spin 4, which is the furthest spin from it. It's fairly strongly coupled to spins 2 and 6. And it's very weakly coupled to the odd-numbered spins. And then spin 1 is likewise coupled very strongly to spin 5, and somewhat strongly to 7 and 3, etc., etc. So this is translated, or it's rotationally invariant. This is a rotationally invariant coupling pattern, and it's furthest neighbor couplings insofar as you can make that work. If I just took only furthest neighbor couplings, that would be boring, because then spin 0 and 4 would make its own separate system totally decoupled from everything else, and then spin 1 and 5 would be another separate system that we wouldn't be interested in, because that's not a thermodynamic limit. So this kind of all-to-all coupling, but a hierarchical coupling, does produce a thermodynamic limit. It's something which has been studied since forever by Dyson. It's called Dyson's hierarchical model. And you should think about it, I say, in terms of a tree structure. This tree structure shows that spins 0 and 4 are indeed strongly coupled, as are spins 2 and 6, as are the other two diametrically opposite pairs of spins. And then these pairs are somewhat strongly coupled, and then the pairs of pairs are very, very weakly coupled. So this is really the more insightful way to think about this furthest neighbor Ising model. It's trying to tell you that it's a tree structure. And this is what's characteristic of p-adic numbers. They're associated with a tree structure. The two-adic norm that I was getting so excited about in the previous transparency is beautifully illustrated on the tree as a kind of nearest, a latest common ancestor norm. The p-adic norm of the difference between 0 and 4 is really small from a number theory point of view because 4 has lots of factors of 2 in it. But from a point of view of graph theory, the distance between these two is small because you only have to go down one level before you meet their nearest common ancestor. Whereas if you want the distance between 0 and 6, you have to go down rather further. You have to go down 2 steps. And the distance between 0 and 1 is extremely far in this two-adic sense because you have to go all the way down to the root of the tree before you can get the latest common ancestor. So I would say any evolutionary biologist who thinks about, what do you call these? Phylogenetic trees, is that the word? Any evolutionary biologist should be thinking about p-adic numbers or ultrametric systems, and well, they actually
also have distances between different generations, like with cousins. I mean, they have, because here I've seen that they are all at the same level.
Yes, that's an interesting question, and I actually don't think the biologists have really gotten into that, that I know of. They should.
They should. I mean, you say my first cousin once removed, so why?
Right. So, right. There are people like Boris Raymond who think about these sort of ultrametric systems.
I mean, in terms of p-adic norms,
yes,
different generations.
Absolutely. You'd say that. Well, the simplest thing to do is to say, at a fixed generation, when everybody has kids at exactly the same time, then the p-adic distance between, let's say, an alligator and an elephant is enormous because their latest common ancestor was a long time ago, whereas between an alligator and a crocodile, it's a small norm because their latest common ancestor is close.
But what about an alligator and a dinosaur? I mean,
oh, you mean this guy and this guy? Yeah, okay, so you could try to do that too. I don't know how far the biophysicists have gone.
No, my question was if you can also formulate in terms of p-adic norms.
Then the answer is really no. Well, we could talk about it. It's certainly simplest to say that this is an approximation of the p-adic numbers. It's a sampling of the p-adic numbers. And then this is some superstructure that gives meat to the notion of what the two-adic norm really is. I think that would be the most conservative answer. Okay, so already we can see that there's something kind of sensible about the two-adic norm. It's just an unusual way of saying something that you wanted to say anyway. But why not just stick with the latest common ancestor stuff? Wouldn't that be nicer? No, and here's why. Maybe I should start with this picture. Dyson studied what he called the hierarchical Ising model. This is just a bigger version of what I drew before, where you see very strongly coupled pairs, and then rather strongly coupled pairs of pairs, and rather more weakly coupled pairs of pairs of pairs, etc. So you have some hierarchy of weaker and weaker couplings of larger and larger clusters. Dyson showed that this type of model naturally exhibits a phase transition at finite temperature in classical statistical mechanics. Nothing fancy. What he did not understand at the time was that, number one, this is a second order phase transition, so it should exhibit some kind of conformal symmetry. And number two, the conformal symmetry that it exhibits is not ordinary conformal symmetry, it's two-adic conformal symmetry. And so that's saying there's more to the story than just the tree and just the latest common ancestor. There's a symmetry group which is built from the two-adic numbers, which tells you what kind of symmetry is realized by the dynamics right near the critical point. And it's not hard to visualize what two-adic conformal symmetry is all about. First of all, if we're in this phase transition limit, we've got a really big system. We've got enormous correlation lengths. So there's a huge number of spins. And every cluster that we want to think about anyway, has a very large number of spins. Two-adic conformal maps map clusters to clusters, but not necessarily clusters of the same size. So a two-adic conformal transformation might map a little guy to a big guy, and vice versa. Or it might be simple, and it maps this guy to this guy, this guy to this guy, and just translates them further along the line. That's the two-adic conformal group. And once you've got that under your belt, you can start writing down, or at least trying to write down, two-adic conformal field theories, which was done by a Russian group. Again, the Russians have been all over this. In the late 80s, they found that the natural adaptation of 5-4 theory to the two-adic numbers does exhibit a phase transition, a critical point. It's very much ordinary Wilsonian RG. You can do Wilson-Fisher calculations. You can do everything you expect to be able to do in 5-4 theory, and it all works, and you get these p-adic conformal symmetry groups. PGL, it really just means SL, SL2, Q2. And correlators, for instance, of spins have parallel fall-off with characteristic dimensions, etc., etc. So, I hope that is enough to convince you that, yes, the p-adic numbers are something that you want to think about sooner or later. Let me go on then to, I think I want to skip this. Let me go on to what string theorists have done about p-adic numbers in the past. And I think I'd like to be fairly brief on this, but it's really worth mentioning. String theory started way back before I was born with an amplitude for scattering 4 particles called the Veneziano amplitude, and it was conveniently written as an integral over the reals of some number x, and then we had some product of absolute values of x and 1 minus x raised to powers which are Mandelstam variables of the scattering amplitudes. That's what the Veneziano amplitude looks like, and I've emphasized that this is the ordinary notion of absolute value by writing absolute value with a subscript of infinity, just to remind you that the number theorists think of the reals as Q infinity. And so you can see what's coming. I'm going to stop using the ordinary absolute value here, and I'm going to use instead the p-adic absolute value and see what I get. That's p-adic string theory. So before we get to the actual calculation in p-adic string theory, let me just tell you why people understood that this was the right thing to do physically. First of all, Veneziano, I think just plucked it out of the air. He realized that the beta function satisfied all the usual analyticity properties required of a 4-point scattering amplitude. But later, people like Susskind and others realized what's going on is you're treating some scattering amplitude like this by conformally mapping it to a disk where these insertions of the particles that come in with the different momenta can mostly have their positions be fixed through use of conformal symmetry. But with 4 insertions, there's 1 particle's position on the boundary of the disk which cannot be fixed, and so that 1 position has to be integrated over as part of the prescription for computing the quantum amplitude. And that integration over the last particle's, the last insertion's position, is what gives you this integral, and therefore the Veneziano amplitude. Anyway, the Chicago school, including the recently deceased Peter Freund, whom I knew very little but admired very much, they suggested what I telegraphed before, that we should try the same thing but with x replaced by a p-adic number, and they found an amplitude whose form can be written explicitly, and it satisfied, as Freund and Witten showed, an amazing identity that if you multiplied up all these amplitudes for all the prime numbers p, it gave you the reciprocal, the original Veneziana amplitude. And that really made people scratch their heads, because this is not the kind of identity you normally see scattering amplitudes satisfying. And yet it comes from a very natural place, which really is a beautiful connection to number theory. So let me go through it briefly. It starts with the Riemann zeta function defined like I've done here. It can be written as a product over all primes of so-called local zeta functions defined as I've written here. And having defined a local zeta function for all primes p, one might be inspired to search for a definition of a local zeta function for the real numbers. And for reasons about to become transparent on the next transparency, this is the convenient definition. Looks quite ad hoc, but it has an amazing property that when you multiply all the zeta functions together, all the local zeta functions, you don't quite get one, but you get instead an amazing functional identity that Riemann was aware of. And you get just enough from this Riemann identity to demonstrate that the product of all the Veneziano amplitudes over all the p-adics gives you the reciprocal, the original Veneziano amplitude. The way that goes is that the gamma function for every p-adic number field and for the reals can be written as a ratio of zeta functions. That's not exactly obvious, but it's true. The beta function is written in terms of a ratio of gamma functions. That is obvious. And so if you just play this Riemann functional equation on the product of all these beta functions, you immediately get what Freund and Witten found. So what they found really is a manifestation of Riemann's identity, which, by the way, is very much connected with the famous Riemann hypothesis. The Riemann hypothesis says that all the zeros of the zeta function occur on the line where the real part of the argument is 1/2. And that makes sense because this function is even when we flip through this line. That's exactly what the functional identity I wrote before says. So here you have it, one of the most famous problems in number theory, the most famous problem in number theory. And it does seem to relate to some property of p-adic superstring amplitudes. Okay, so now, in the remaining time, let me tell you about p-adic ADS-CFT and try to get back to this notion of geometry. So, in ADS-CFT, schematically we have some boundary, which maybe is the reals, or maybe it's R2, and then we have some curved bulk geometry in which supergravity lives. That's the scheme. For p-adic numbers, you've kind of already seen what the story is. You have the p-adic numbers up here, and then the sort of superstructure that's below them is a tree. This can be made formal in a beautiful mathematical way. I'll just say it out loud rather than walk you through it. The quotient of the two-adic conformal group by its maximum compact subgroup is the tree, just as ADS2 in the Euclidean case is SL2R mod U1. So the tree is a tree for the reasons that I was explaining in connection with latest common ancestors. It tells you about the two-adic norm. But you can motivate it through wholly group theoretic reasons. And you can, as I was trying to suggest here, you're not limited to one dimension of the boundary. You can have multiple dimensions in the boundary. And so I think, in the interest of time, let me go straight for what I really want the most, which is some notion of geometry on this graph. Because here we have fluctuating, well, not here. In 2 dimensions, the Einstein action is topological, so you don't really have a good notion of fluctuating geometry. Even in 3 dimensions, it's a little fudgy. But eventually, in 4 dimensions and higher, you have fluctuating geometry in the bulk. And so what would we do to have at least some kind of dynamics of geometry on a graph? So to that end, I will skip over a few things I'm happy to return to. What about gravity on the graph? Well, let's do the only thing we can do, it seems, and say that each edge, I'm going to think of an edge as joining 2 vertices x and y on the graph. Each edge will have some length, which is axy, and I'm thinking of axy as just a real number. So an inch, a centimeter, some length. And so I want a dynamical theory of the axy's, which will somehow prefer constant axy, a regular tree, as a solution of its equations of motion, but it will allow some fluctuations of the axy's that will be interesting. And I want this dynamical theory of lengths to be as similar to the Einstein-Hilbert action as I can contrive. And so what I claim, without further ado, is that what you ought to do is sum over all the lengths in the graph a funny-looking expression, kappa xy, which is a rational function of these axy's. And that rational function is this monstrosity. So it's not much to look at, and I admit it doesn't particularly suggest itself as an obvious generalization of the Ricci scalar. But we didn't just make it up. We claim it's a good idea, although possibly not a uniquely good idea. So I'll explain where I got this and a couple of its good properties, and then we'll leave it at that. I'm sorry that I can't go further. Obviously, what I'd like to do is start with this action, a dynamical theory of these lengths, and tell you that somehow I've reformulated quantum gravity in a way that's now tractable. I'll point out one feature which is tractable at the end, but I can't go very far in the direction I would like. Okay, so why did I write down that kappa xy? There really is a good reason. I'm going to write down a way of computing the Ricci tensor on an ordinary smooth manifold, which extends very naturally to the graph and gives me my kappa xy. Here it is. First of all, you start with a distance function between 2 points. That I surely have on the graph. It's how many steps I have to take along the graph to get from x to y. I also have that on a smooth manifold. It's the geodesic distance, provided I'm on a Euclidean signature. Okay, I really need Euclidean signature. So okay, I have a distance function, and the next thing I want to do is to promote the distance function to a distance between any 2 probability distributions in such a way that if the probability distributions are strongly peaked near individual points, then the distance between the probability distributions will be very nearly the distance between the points. So here are 2 probability distributions rather like what I want. Here's the one centered on the blue point, here's the one centered on the orange point, and so surely the distance between these 2 probability distributions should be approximately this distance here. But exactly what should that distance be? A natural definition, one that is in common use in mathematics due to Olivier, is this slightly funny-looking thing. It basically says, pick a function which has slope no greater than 1, and is as positive as you can make it over here, and is as negative as you can make it over here. So it's a function that spreads out between this probability distribution and this probability distribution as much as it possibly can, subject to the constraint that its slope is never bigger than 1. So here's this promoted version of D promoted to taking arguments which are probability distributions. So why did I do this? Or why did Olivia do this? It's because if you take one more step, you can get something very naturally that gives you the Ricci tensor. The one more step is to consider some kind of diffusion process. On a smooth manifold, a smooth Euclidean manifold, imagine some diffusion process. Time here is just some external time, like a stochastic time. And the solutions to this are probability distributions that start very localized at individual points and then spread out a little bit. Like I indicated here, it starts at some point, then the probability spreads out a little bit into some region whose typical size is the square root of the time.
Sorry, that's the Laplacian operator, not the wave operator.
Indeed, this is yes, right. This is the positive definite Laplacian operator, and yeah, emphatically in Euclidean signature. So it's the sum of d by dx squared over all the Euclidean coordinates.
Your distance before that is this Earth mover's distance or Wasserstein distance? Is there the one that you defined on the previous slide?
Yeah, my dx x1 x2 is given, and then my d. Oh, you're talking about this dp1 p2. Yes, yeah. That's the Wasserstein distance. Yes. So anyway, I inquire what the Wasserstein distance is between two slightly diffuse probability distributions that started at points x1 and x2. Because they're only slightly diffuse, the first guess is that this will be equal to that. And the correction involves the Ricci tensor. Not too surprising. But what's interesting is that if you know the corrections for any separation direction n, you can reconstruct the entire Ricci tensor, because the Ricci tensor is a symmetric tensor. If you know this quantity here for all unit vectors and mu, you know the Ricci tensor itself. And this is a nice intuitive local definition. It's intuitive because the way diffusion works on a curved surface is that if it's positively curved, then diffusion is kind of slower than you think it's going to be. You start diffusing normally, as if you're on flat space, but then the surface starts closing in. There's less of it than you thought there would be because it's positively curved. And so you don't diffuse as well as you thought you would. And that's this term. Positive curvature means that you're not diffusing as well as you thought you would. Whereas if you're on a negatively curved manifold, it opens up like crazy. It's exponentially growing, and so you're going to diffuse faster than you thought you would as a flat space thinker. And that's why, with negative curvature you get a positive correction term. Okay, so you can see where I'm heading. I'm just going to do this on a graph, and it looks a little abstract, but it's no different from before. I start with, let's say, a bunch of blue ink here, and then I let the blue ink diffuse just a little bit so that you get a little blue ink here, here, and here. And likewise, I start with some orange ink and let it diffuse, and then I ask how much do the blue ink and the orange ink overlap, more or less. And that's this Wasserstein distance, and that gives me some natural notion of the distance between the probability distributions P1 and P2, which then gives me some notion of this Ricci curvature times a separation of the 2 points. And that's how I got kappa x1. So, like I said, I claim it's a good idea. I would not claim it's a uniquely good idea, because you could imagine cooking up some other way of defining Ricci tensor on a graph. I think you might be hard-pressed to get a better way, but there might be other ways that are as good or as natural. So I said I was going to tell you one or two good properties of this notion of dynamics on a graph. So first of all, its equation of motion is pretty simple. Its equation of motion looks like this, which is still a little abstract, and this, still a tiny bit abstract, but then these are very natural things. These are sums of inverse, in this case, squares of distances from a given vertex to all its neighbors. So it's basically saying how well connected is this vertex X to other neighboring vertices Y. And there's different ways of measuring that according to the square, according to the first power. Okay, so that's just what comes out of it. And you can show from this simple equation of motion that yes, the regular tree is a solution. That was a sine qua non. So that would be like saying ADS is a solution of the Einstein equations with cosmological constant. Hooray. Further, you can show that small perturbations away from the regular tree obey some kind of massless Laplacian condition. And that means eventually that the two-point function of the stress tensor is going to have the right power law for an n-dimensional theory if your boundary is n-dimensional. And the last property, the last thing I want to say, is that this action has a positivity property. The action I wrote, you remember it was the sum over all the lengths of kappa xy. You have to add some boundary terms like you always do in Einstein actions. Once you've added the boundary terms correctly, this action is bounded below. And I mean, I even showed it on this transparency. I feel like maybe that's redundant. So perhaps take my word for it. I can answer questions based on this slide on exactly why it's bounded below. The action is bounded below, and the very best possible least action configuration is the regular tree. So that's dramatically different and better compared to the Einstein action, which has a notorious problem that the so-called conformal factor on the metric has arbitrarily negative modes. So there's never any such thing as a least Einstein action solution. You always have extremely negatively curved directions that you can go in. And for non-perturbative gravity, that seems like an awful thing. Here we have the opposite situation. And it seems to me, therefore, that a Euclidean path integral formulation of this graph theoretic quantum gravity is bound to be well defined. I can say no more. Like I say, I wish I could. But I can at least claim that there's something on the horizon here that is promising a well-defined path integral formulation.
So there is no obvious way to take a continuum limit and recover Einstein.
I agree with that. Yes, that's right. And it's the frustrating thing is I would have to answer we're not even trying to do that because the tree is already a full realization of p-adic conformal symmetry. You don't have to take a continuum limit of the tree to get that symmetry. Like in a tensor network in ADS, you're sampling ADS at discrete points. So you're not catching the full isometry of ADS. But the tree does capture the entire p-adic isometry. So that's why I would answer no continuum limit needed. I'd like to look on the bright side and say that another way to look at that is that there's a natural length scale. You're not supposed to take a continuum limit with these p-adic trees. So there's a potential opportunity of escape from the ultraviolet disasters of quantum gravity, which is that you have a natural discreteness of your geometry.
But can you measure it in centimeters?
Well,
I mean, it's bigger or smaller than L Planck.
Clearly, the guess would be this is, if it's happening at all, it's happening at order L Planck. And so this is where the Russians want to go. They want to say that when you get to the Planck scale, Riemann's dream comes true, and smooth geometry dissolves into some kind of p-adic something or other. I'd like to refine it and say, well, maybe there's some kind of tree structure that takes over. But I can't put meat on the bones of that assertion. So let me be careful in what I can and can't do. Anyway, what I would like to say is that being invested in the subject, I hope that p-adic ADS CFT is the tip of a big iceberg. It certainly reorganizes your notions of geometry somewhat. And there are lots of ADS CFT-like calculations you can do. I focused on gravity, but you can do correlation functions, endpoint correlation functions, loop diagrams even in ADS are in progress. Some of the things we can't handle yet that we really wish we could are understanding spin in the p-adic ADS CFT setting, and especially understanding Lorentzian signature. And in recent months, I've also been starting to hope harder that we might get some interesting experimental realizations of p-adic conformal symmetry a little bit along the line of these hierarchical models. And I've been discussing things with a Stanford professor named Monica Schleier-Smith, but I think that'll have to wait for another talk. Thank you for your attention. Yes?
I think, if I understood correctly, so the action will be limited in this.
The action has a lower bound, yep.
Yeah, so therefore, because in Einstein, if I take the sitter, action is infinite. So it would be interesting to see what's the bound. How does it translate to the, let's say, action of the universe?
So I had to be a little cagey there because the boundary terms matter a lot. And because when you cut off an angle to curve geometry generally, there's as much sort of area as there is volume. In a graph,
This for the ADS.
that's right.
I know I had in mind, you mentioned this about the scale factor instability.
Yes.
These arbitrarily large action.
Right.
And that's, of course, this translates as the fact that the sitter, the kernel of the sitter is an infinite action. But this, so
right.
if you apply your thing to the sitter, probably you would get a finite.
But I can't, because I like I say, I really need I really need Euclidean signature so far to understand what I'm doing.
Because that would be great.
There are some proposals for instance, treating all legs as null, but I don't quite understand how the overall geometry is going to come out when you do that.
Yeah, because that would settle the issue of this eternal, for instance, the eternal universe or whatever. If there is a limit to the action, then that's it. The universe is fine.
Yeah. Okay. So, we can think about it, but the big stumbling block, like I say, is that at least so far, I have not been imaginative enough to get my head around Lorentzian signature. Maybe it's just a tactical limitation that I'm so attached to these Wasserstein distances that are based on supremums and so forth.
Matt.
So you mentioned that P here is 3 is the number of nodes that are splitting off, the number of branches that are splitting off.
That's right. This is every time we go outward, we're branching threefold. Previously, I was usually writing it twofold, so this boundary is going to be based on the 3 atoms.
So can you generalize this to allow different numbers of branches?
So at some level, yes. Anytime you have a tree structure, you should be able, for instance, to define a latest common ancestor norm. That seems like absolute common sense. What is much less clear is whether you can get any kind of understanding of the conformal group. Look at it this way: the way the conformal group, these linear fractional transformations over 2 adics, the way it works, the way it acts on the tree, is to map sites on the tree to one another in such a way as to preserve nearest neighbors. If you have a tree that does not have a constant coordination number, well, then you better you're going to have to restrict your isometries by a lot. If it has disorganized coordination number, it probably has almost no isometries whatsoever. The tree. So it's not. Yeah. So I think you're going to cut down your symmetries by a lot, but there might be some approximate symmetries. I'm not quite sure what to say.
So if I followed the logic about this kappa and Rashid, you put some mass somewhere and you let it diffuse, and you said if it's curved, then you see what happens to these distances. But there's a bunch of other families of distances between probability distributions. Didn't seem like it really mattered as long as it got smaller or bigger based on the curvature. Is that correct? Or was there anything special about Wasserstein?
So this is why I was so cautious to say that this is a good way of coming at the question of what is curvature, but I don't claim that it's uniquely good.
Right, but I mean, if I pick a different one where it still keeps the same, correction, then it would the logic about how you connect to this kappa to
yeah,
the
all right.
same, right?
So then I think we would want to qualify a little bit on how we measure good. So for instance, at the end of the day, in my story, the kappa xy involves links that are only neighboring the link kappa link xy that I'm focusing on. So that kind of makes it like a second derivative quantity. So whatever version of curvature we wind up with some fancier notion of, or other notion of distance, I'd like it to have the same property, or else I would call it a higher derivative correction.
Yeah, I mean, I think most of the ones I think of would just stick in that first part would be leading term would be the same.
Yeah, it could be exactly that. That there's a lot of versions that give you the same leading term correction, but then I would say they give the same cap xy.
And then also the probability that it's not over some continuous x, it's now like discrete things on the lattice sites, is that right?
Yes. Yeah, so the way we like to say it is that the curvature, the Ricci curvature is defined on a link.
Questions?
So if there's some sense in which the p going to infinity limit is the real numbers, can you take p going to infinity of your kappa and see if you get the real answer?
In fact, maybe I can ask a related question, because it's a refinement of this. The amplitudes are a product of all the p-adic amplitudes. I mean, the string amplitude is the inverse of the product. So do you have to take the continual limit? Do you have to take p to infinity, or take a product of these different?
Yeah, so those are all good questions, and we feel like we don't have nearly as much understanding as we should. So first of all, these products, there's versions of them that we can do that give you very simple answers. For correlation functions, typically you multiply the correlation function together across all the primes and the reals, and you get something that's independent of position, as if it were a topological theory. That's the kind of characteristic feature of these products over all primes and the reals. But actually, there's another limit which I think is at least as interesting, and that is formally p goes to 1. Samson Chatashvili and friends have played this one up, and the reason they like it is that in the space-time of the p-adic, the space-time effective theory of the p-adic string, the tachyon has an action that looks like this, and if you expand around p equals 1, then this turns into, and it has a mass term. Then it turns into phi box phi plus some adjustment to the mass term. I think that's, well, we can get into it more later, but I think there's some reasons to think that this limit is the more sort of physical way to imagine getting back to the reals.